Hope everyone's been having a good day. Another wonderful day of online learning. Everybody's favorite. So that's right. Bow tie Tuesday. All right, I told you it was going to happen. Right, we're geared up. We're ready to go. All of you, if you're watching this at home right now, whether it's on Twitch or YouTube, you should 100% be wearing a bow tie as well whenever you're watching this. Right, it's a requirement for the stream. Right. Make sure to use the bow tie emotes, and we'll be good to go. We're not right now. I appreciate the support. See, we all gotta, in these trying times, we need signs of solidarity that we can come together and all wear bow ties together, and that is what is going to get us through this. That will save the human race, probably. You know, based on my scientific research that I've been doing. So it's fine. All right. So let's go ahead and kick this off. Starting off where we were yesterday on solving the exponential equations. Max here to vibe. Great. Wonderful. Solving the exponential equations. So we talked about this yesterday in when we have an equation where both sides are just some exponential and how we go about dealing with that. Now, our goal is to first look at trying to get the bases to match on either side. Right? On one side right now, I have a base of 36. On the other side, I have a base of 1 over 1,296, a great base, one of my favorite numbers. But again, if you're worried about the fractions, you freak out about the fractions, then don't bother with that just yet. Let's first focus on 1,296. Now, I don't know about you guys. I don't know a lot of information off the top of my head about the number 1,296. Okay, it's not a number that I, have just in my brain of, oh, I know this. These powers make this, or these are the factors of 1,296. Okay, but when I look at 36, I do know some stuff about 36. And remember, so we're trying to think about powers here. So I know that 36 is the same thing as 6 squared. And I'm not sure that there's any other power that makes 36. Okay. So I'm thinking then, all right, I'm probably pretty sure that my base is going to be 6. I just need to figure out 6 to what power is going to make 1,296. All right, so we're going to have to do a little bit of guess and check on our calculators. Let's see. I know it's not 6 cubed. Let me just go up one, 6 to the 4th. And so, yeah, turns out 6 to the 4th power would make 1,296. Right? Now, that's a good start. It's not exactly what I want. Nice, Phoebe. Because since there's the 1 over that, we're just going to switch it up then by making it negative. So 6 to the negative 4th power then would make 1,296, exactly what I want. So now that I know these, I'm going to go ahead and rewrite my problem, rewrite my equation so that it's written with these bases of 6. So instead of 36, I write 6 squared. Instead of 1 over 1,296, I write 6 to the negative 4th. Wonderful. From there, so now we have powers of powers. So we remember our exponent rules. Whenever we have a power of a power, we multiply. So in this case, don't forget we're going to need to distribute on both sides. And don't forget with the negative to distribute the entire negative 4, not just 4. All right, draw your little lines if you need. Helps out so you don't forget. So 6 to the negative 8x plus 4 equals 6 to the 6 minus 2x. And that's great because once we're here, our bases are the same. We can just forget about the bases altogether. Let's just focus on, well, we know we need those exponents to eventually be the same thing. So what value of x would make that the case? So let's just look at the exponents and set those equal to each other. Negative 8x plus 4 equals 6 minus 2x. And then it's just a matter of solving. Right, I'm going to bring my x's to the right side. So negative 2x plus 8x would be 6x. 4 minus 6, negative 2. All right, so just 2 and 1, moved my x's to the right side, moved all my constants to the left side. And then divide by 6. Of course, we always simplify if we can. So x equals negative 1/3. So just getting in that habit of, I see an exponential on both sides, then my first hope is that it's this type of equation where I can get the bases to match up, where I can make it so that it's same base on both sides, and that's it, and then I can just go ahead and solve. Good deal, good deal. As always, just let me know if you have a question. Just put a quick note in the chat, and I will know to stop or pause. Oh, Austin, I did not see that you also got the fish tank that you emailed me about. I did want to take this time to thank you for emailing me about the fish tank. Yes. So, and I'm super glad now that you actually have the fish tank as well. So this is another big move, not only for you, not only for us as a class, but I think for humanity in general. So well done, Austin. The math analysis chat is so chaotic compared to this one. Are you sure? Math analysis? No, that one was tame yesterday. Maybe the calculus one. That's where things get rowdy. Okay, so we're going to talk today about logarithms. And it's just, we're going to do a little bit about logarithms. We're going to come back later on in the unit to do some more in-depth logarithm stuff. But for right now, we're just going to kind of get a basic idea of what a logarithm is and how we can use it for some more exponential equations. Right. So a basic of a logarithm is this is kind of our key fact here. That logarithms are the inverse of exponential. So you guys know about inverse operations like addition and subtraction, multiplication and division, things like that. So if I'm talking about an exponential, so something to the x power, and I want to get rid of that base, whatever it is, then I have to use a logarithm. Okay, because it's the inverse, right? In the same way that if I'm solving an equation and I see that there's addition, well, I need to use subtraction to get rid of that. Or if I see that there's division, I need to use multiplication to get rid of that. Right? And so my second point here, it's what we use to get x or any variable, because we solve for any variable, not just x, out of an exponent. So if I have some variable that's trapped up here in the exponent, and I need to do something so that I can untrap it so I can get that 3 out of there. I can't just divide 3. I can't just subtract 3. The only way to bring that x down is I would have to use a logarithm. Right. But before we get into that too much, let's just look at what a basic logarithm can look like. So here's an example. The way that I would say this is log base 2 of 8. So whatever that little number is down below there, we call that the base of the logarithm. So log base 2 of 8. And all that this means, people freak out when they look at logarithms because it, maybe looks strange. There's 2 different numbers. There's these weird letters, and but it's not so bad a lot of times. So log base 2 of 8 is something that we can do in our heads, because all this is asking is if we start with the number 2, what exponent would we have to put on top of the 2 in order to get 8? So when I look at this log base 2 of 8, really what I'm thinking in my head is this is asking me, oh, okay, 2 to what power would make 8? Well, being the super smart students that we are, we know that 2 to the 3rd power makes 8. And so that's all a logarithm does, is it sort of works backwards from a normal exponent. So instead of saying this number to this power equals this number, the logarithm gives us the starting base and it tells us what the final answer should be. And what it's asking for is what is the exponent that should go on that base to make whatever's inside there. So in this case, 2 to the 3rd power makes 8. Another quick one. Log base 3 of 9. So again, what this is really asking me is 3 to what power makes 9? Hopefully we're all well aware that that's 2, because I know that 3 to the 2nd power is 9. And then just one more slight mix-up. Log base 4 of 1/16. Okay, so now this is asking me 4 to what power makes 1/16. So this is sort of similar to what we solved about in our warm-ups when we're thinking about these bases and these powers. And so yes, exactly, Aiden. So first think about what power would just make 16? Well, 4 squared would make 16. Well, then if I want the 1 over 16, then we use our exponent rules of saying, oh, okay, so a negative exponent would then drop that down into the denominator. That's exactly what we want. Okay? So again, don't freak out about the fractions. All right? Just know that if you need to bring something down into a denominator, some sort of power, we can use negative exponents to do that. It's fine. Okay. All right. So now how can I actually use this to solve equations? All right, so that was just the basics of how a logarithm works, but we're going to use logarithms mostly to solve equations. All right. So for example, I have a very basic equation right here. 5 to the power of x equals 13. So we always say when we're solving, get the x by itself, or get the w by itself, or the t by itself, or whatever the letter is. Who knows? We want to get it by itself. And usually we're used to just knowing what operations we need to do that. Divide, add, subtract, multiply, whatever. But it's a little bit different if this x is trapped up here in the exponent. Right? Because I can't, so again, I'm going to write a couple things here that I should not do. Right? I can't just divide 5. That doesn't work. That wouldn't, I can't subtract 5. That wouldn't work either. Right? So since this is an exponential, we need to use whatever the inverse of an exponential is. And in this case, we know, like we just talked about, inverse of an exponential is a logarithm. Right? So I'm going to use a logarithm on this equation. And like any good math operation that we do, whenever I do something, I'm going to do it to both sides of the equation. So I took both of the things I had originally, but then I put them both inside of logarithms. Now there's one more thing I need to do here, which is right now I didn't put a base for either one of these. Okay, so I do need there to be some base. And a lot of times people get confused about, well, what do I make that base? Well, it should just be the same base that the base of the exponential was. So in this case, the exponential of or the base is exponential. The exponential's base, there we go. That's the words I want, is 5. So I'm going to use base 5 for these as well. So the reason that I do that is because I now have a logarithm base 5 and an exponential base 5. And so when I have that base 5 exponential inside of that base 5 logarithm, what happens is those cancel each other out, and it will just leave me with the x. Right? I got rid of the 5, so now there's just that x. I essentially kind of brought it down out of the exponent and managed to cancel the 5 by using a logarithm base 5. Now on the right side, yes, question. Do you always have to do this step? No. Well, it depends on what you mean. I mean, if we need to solve, then yes, we need to use logarithm. Do you need to actually fully write out like the... Oops. This part where you do log base 5 of 5 to the x, and then just to cancel the logarithm in the 5. I think that's what probably you're asking. No, I don't think so. You could go straight to this. If you know that you're using the logarithm on both sides and you know it's going to cancel anyways, then no, I don't need to see that written out. No, that's fine. just doing it on here to show exactly what's happening, but you don't need to do that part, or at least write it out. Good question. Good question. Okay. Now on the right side, log base 5 of 13. So again, sometimes we can do logarithms in our head. So since this one is just numbers, I'm still going to think log base 5 of 13. So that's basically saying 5, not to the second power. 5 to what power is 13? I always forget you guys can't see that part. Five to what power is 13? Well, I definitely don't know what that is. All right, it'll be some, 5 squared is already 25, so there's no nice number here. It'll be some decimal or fraction. So never mind. I can't do it in my head, but I do always want to check to make sure that it's not something that's easier that I could just, instead of having to write log base 5 of 13. If there's a better, more simpler answer, then I'd like to write that instead. But in this case, we don't have that. And so like Abby asked, just to reiterate, if we were doing some solving in an equation and we just went right to here from that step, that's totally fine. I'll keep writing out, at least for this lesson, I'll keep writing out the full like log base 5 of the 5 to cancel it, just to show you guys what's happening. But I don't expect you to write that every time. Okay, so let's bump it up a tiny bit. Can we solve the logarithm with a calculator? Do you mean like this? Do you like type that in and get a decimal? Is that what you're asking? Come on. Are you asking me about a decimal? Come on. Come on. You know how I feel about decimals. So I mean, you could get a decimal, but I want this answer. I know it's not the prettiest thing, and we're gonna have some really ugly answers here coming up, but log base 5 of 13. I'm 100% fine and want that answer. Unless we'll do some word problems later on in the unit where we will actually get decimal values, but if we're just solving an equation, no. Even though the world has turned upside down everywhere else, I still hate decimals. So there we go. Solve the equation. So 4 to the x minus 9. Very similar problem. Except now in the numerator I have x minus 9. I have an exponential on the left side. The right side is just a 7, so that's not an exponential. It's just a constant number. On the left side, I have this exponential that the base is 4. Well, I know that to get rid of exponentials, I have to use their inverses, which is a logarithm. So I'm going to use log base 4 on both sides. Just take both sides of the equation and put them inside of logarithms. And then since these bases are the same, a logarithm base 4 and an exponential base 4, then that means I can just cancel those, leaving me with x minus 9 equals log base 4 of 7. So again, real quickly to myself, I think 4 to what power makes 7? I don't know. Right? It's going to be some sort of decimal, so I don't want it. So I will just continue to write log base 4 of 7. Solve for x, so I'll add 9 to both sides. And that will be my final answer. Right, make sure you don't, the 9, we can't actually add the 9 to anything. Sometimes people try to add like the 7 plus 9 to make 16, like log base 4 of 16. No, that's not how it works. The 7 is trapped inside of the logarithm, so we cannot combine that with the 9 in any way. All right, so we just write, this is our final answer, and that's okay. All right. Let's, before we crank it up into more, let's talk about a number really quick. You guys know how you love numbers so much. Me too. So this guy is, now I know it's not, it doesn't look like it, but it's pronounced Euler, right? Almost like O-I-L-E-R. Okay, Euler. Not Euler. If you say Euler, you're embarrassing yourself in front of the mathematical community if you say Euler. Come on, guys. You're more sophisticated than that. All right. So it's Euler. How dare you? is this guy hundreds of years ago, and he did a ton of stuff with math. He had so many things named after him. Exactly. And funny story, actually, he ended up inventing so many, or not inventing, but he ended up discovering so many things. Euler's method of approximating derivatives. Oh my gosh. He ended up discovering so many things that it turns out they got sick of naming everything after him. They would name numbers and equations and various things after him in different fields of, math or physics or whatever, science. And so eventually they were like, okay, Euler has too many things named after him. We can't do this anymore. So they started naming things after the second person to discover whatever the equation or formula or identity was, just so that not everything would be named after Euler. So big shout out to all those people who came in second place in discovering something, but still ended up having it named after them because they decided to stop naming things after Euler because he was too famous. Classic. So Euler's number comes from this expression, 1 plus 1 over n to the nth power. And so what happens here, I'm going to bring up Desmos here. So the graph is not important. Well, I mean, yeah, not really. So I'm just going to see what happens if I take that expression, that 1 plus 1 over n to the nth power, and plug in different numbers. So if I plug in 1, we would get 2, which makes sense. If I plug in 10, I get 2.593. If I plug in 100, I get 2.7048. If I plug in 1,000, okay, I still get 2.7 something. 10,000, I still get 2.7 something. Those numbers afterwards are changing, and 100,000, okay, same thing. Or 1,000,000, or however many zeros I want here, whatever. But the point is, we can see, even though I'm typing in such hugely different numbers, my end result really doesn't change that much. And actually, it changes more so from like 2 to 2.5 up here. But down here, like these numbers, like these last two are the same all the way through like this 8. And then they're slightly different. So what happens is, as n gets larger and larger, or as n approaches infinity, just typing in larger numbers, this expression becomes a specific number. And that number is E. Let me bring back my notebook. So that number becomes E. You should all have an E button on your calculator. It might be, sometimes it might be like the second or shift that's behind the LN button, which we'll also talk about in a little bit. But you have E. E is like pi, where, yeah, I get that it's a letter. It's not a number, but it represents a number. Just in the same way that pi represents 3.14, whatever. E represents 2.71828, etc. Right? They're both irrational numbers that the decimals continue forever and ever and ever, and they'll never stop. And they're just so wonderful. Okay. So we get E. Euler's number. Don't let me down here. Don't let me down here. Euler. Say it with me. Euler. Very good. Okay. So there's a couple special logarithms. And the first of which is called natural log. Natural log is just a logarithm that is base e. All right, that wonderful number that we just figured out. And the way that we write natural log is instead of writing log and then the little e below it, okay, we write it like this, ln. I always write it with a cursive L, just so, I mean, you can write it like this if you want to, but I always write it with the cursive L so that I don't, mix up the L with like a 1 or whatever else. It's just more clear to me that I'm looking at ln. So I always do the script L. So again, what this represents is just a log base e, but we don't write log base e. It's just one of those things that we decided instead of writing that, we will write ln. Right? And that's what that ln button on your calculator is. Common logarithm is a base 10. And the way we write that is actually log, but we don't put any base at all. Okay, so we do not need to write the 10. So instead of writing, log base and the little 10 of x, okay, no, we don't need to write that. We can just write log. And so anytime we see log, just log, and there's no number below it, we should just automatically know, okay, this is base 10. Right, it's just another thing. As a society, we have decided that we will make that base 10. Right, we don't need to write the 10 there. In the same way that if I have an x, I know that there's a 1 in front of the x, but we have just decided we don't need to write the 1. We know that the 1 is there. So kind of the same deal for common log. We don't need to write the 10. We just have to know it's there, right? That it's a base 10. All right, so those are nifty and will help us solve some more equations, but let's first go back to kind of solving one in general. So I have this exponential equation that I want to solve. My goal when I first look at this should be to isolate the exponential. So this yellow part that I highlighted, before I start worrying about logarithms and stuff, I just first need to get this by itself. All right, so to deal with that, I have this pesky +4 that's hanging on right now, so I want to get rid of that. Subtract 4 on both sides. So I didn't use any logarithms. All I did was subtract 4. But now, since I have a base 9 exponential, 82, yeah, what the heck. Thank you. Now that I have a base 9 exponential, in order to get rid of the exponential, I need a logarithm. So, like I've been doing, logarithm on both sides, and specifically, since the base is 9, then I know that I need to use 9 as well as my base. Okay. And the stuff that was on the inside just stays on the inside. Log base 9 and the base 9 exponential, they cancel each other out. So I have 2x minus 3 log base 9 of 82. Log base 9 of 82, I can't do in my head. 9 to what power makes 82? I don't know. I know that 9 squared is 81, Maybe that's what I was trying to do when I messed up before. But it's close, but it's not good enough. All right, so I'm just going to leave it written like this. And like Abby asked about earlier, again, I'm totally okay with you guys going straight from that first line that I just wrote down to here. All right, no problem. Add 3 to both sides. And then divide 2. So this is what I get as my answer. Again, certainly not the prettiest thing, but it is my answer nonetheless. All right. Let's check out our next one. What do we got? 2 left. Okay. Let's check out our next one, which not too wild, but does have some interesting pieces. So again, our first goal. So this highlighted portion is my exponential, right? The e to the 2x plus 1 is the exponential. So remember, like I said for the last problem, before we start worrying about like logarithms or anything like that, we first have to isolate the exponential. Right now, it has this coefficient of 3 on it, okay? But I don't want that 3 there. Before I can use my logarithms, I want to get rid of the 3, move it away, so that I have just the e to the 2x plus 1. So no problem. Let's just start off by dividing. Okay, so divide both sides by 3, so I get e to the 2x plus 1 equals 17. Now that it's just the exponential, I can use logarithm now. So my logarithm, because my base is e of the exponential, then that's the same base that I want my logarithm to be. But we remember that's one of our special. Base e is a special logarithm. So we're not going to write log and then with the little e down below. We're going to write ln. Because ln means log base e. Question, Yeppers. If you write log base e, is it wrong? Yes. I understand what you mean, but no one anywhere ever in the world writes log base e. Okay, so this is incorrect notation. The correct notation is to write ln. Anybody that writes this, I think you already know what you have to do. You have to play rugby. Okay, so take that into consideration. Same thing goes for anybody who pronounces Euler wrong. Would you count us wrong on a test if you wrote log e? Yes, I would mark it Like if I were grading it to send it back for corrections, yes, 100%, I would mark that. That's right. Okay, you guys are finally starting to see how high the stakes are here. Okay, this could be your future, so be careful. All right, so in our solving, the natural log and the exponential base e cancel each other out. 2x plus 1 equals natural log of 17. I definitely do not know e to what power would make 17, so I'm just going to leave it as natural log of 17. Subtract 1 from both sides. And divide both sides by 2. Oops, not 2. Come on. There we go. So it'll seem weird at first, but you'll get used to the whole ELN, especially for LN. We are going to use LN so much. This is maybe one of our most common looking equations that we'll use whenever we do our word problems and application problems later on. We're going to be doing stuff that has E in it a ton. And so it'll be like second nature that we're using ln and not writing like log base E. So it'll be fine. It won't be like some random weird rule that you have to remember. It'll be something that you become really accustomed to because we're going to do it a lot. All right, last equation. 15 minus 2 times the 10 to the power of 3x plus 5 equals 11. All right, there's a lot going on in this problem. This will definitely be our ugliest answer, but that's okay. So first think about what we're doing. So this is my exponential. So before I worry about logarithms at all, isolate the exponential. So my first goal I'm just going to get rid of that 15. By subtracting 15 on both sides. 11 minus 15, negative 4. I'm going to divide both sides by negative 2. Negative 4 divided by negative 2, positive 2. And so now I have an exponential that is base 10. So I have to ask myself, how do I get rid of an exponential that the base is 10? Again, it's not dividing 10, it's not subtracting 10, it's an exponential 10, so I have to use a logarithm. And specifically, I have to use a logarithm base 10. Okay, but remember, logarithm base 10, that's our common log, what we call common log, so we don't need to write the 10 there. All right, we're just, again, this is a thing where the correct notation is to just write it without the 10. And whatever was originally there just stays on the inside of the logarithms for both sides. Common log and logarithm base 10 cancel each other. 3x plus 5 equals log of 2. Now it's just solving for x. Subtract 5, divide by 3. So there's our final answer. All right, so again, we're going to use these for a ton of word problems, various things later on. So we just got to get good at making sure we're okay with solving the equations so we feel comfortable with that, because we'll need to do it over and over and over again. But I think that was, yeah, definitely. That's my last one. Okay. So any questions I can answer? This makes a lot more sense this year. Okay, good. Yeah. Definitely helps that it's the second time that you're seeing some of it. But good. I'm glad it's making sense. So whenever the base is 10, you just write log. Yes, absolutely, Selena. 100%. Just instead of, I mean, if you need to in practice, write the 10 just so you know it's there, and then maybe, again, I don't want you to leave it there, but maybe do it while you're solving and then just go back at the end of your problem and erase it from your final answer. Like, I'd be okay with that. But yeah, so whenever the log is base 10, you just write log. Exactly. All right. I guess that's all we got then. Are you guys bored of being at home yet, or feeling good still? We're on what? So spring break from last Friday. So 2 days a weekend, 5 days, 2 more weekend, 9. So this is day 11 of you being at home, right? Tough times. We only got, yeah. I feel you. Right, but I'm sure you're using this as a great opportunity to, enrich yourself. You have tons of time, learn some new skills, practice something in your hobby, learn a new language, read some books. If you got any really amazing book recommendations, send them my way, of course. We only have a month left. Yeah, that easy. Selena, you don't know how to read? Well, yeah, you'll get there. You'll get there. I believe in you. That's what I'm saying. This is your opportunity. You can learn how to read now. For like 16 hours straight, man. I think that's technically called a coma. But yeah, maybe. Throne of Glass by Sarah J. That's best book series ever. Okay, I'll look into it. We'll see how it goes. Watership Down. I've always heard it talked about. I've never actually read it though. I might have to go check that out as well. The little train that get it. That makes a lot of sense, Austin. I think that's a great message